Good evening, everyone. Thank you very much for joining us today. My name is Koji Yamamoto. I'm a developer and a material engineer at Cybernet Systems in Japan. I am delighted to be here to talk about our solution. Cybernet is an Ansys channel partner in Japan and other Asian countries for many years. We have developed several CA software in-house as well and worked with NCSoft to provide services for those products. Today, I will be talking about the introduction to Multiscale extension for Ansys Workbench product, which is one of our original software. I hope today's presentation will help your business. My presentation will be going on according to this sequence. First, I'm going to talk about the background and motivation of our work, reviewing some of the technical issues of composite materials. I will show you that the approach to CA analysis of composite material is different from that of metallic materials. There are many issues that need to be cleared before starting the analysis. Our Multiscale tool will be one of the effective solutions for this. This is the second topic. I will introduce about our original Multiscale solution, which is add-on tool for Ansys product. I will show you the overview of each feature and some of capabilities for coupling with other tools. As a final topic, I will show you some of the analysis examples by our product. Today, I will introduce only a limited number of analysis examples. Our company are planning to hold the webinar 4 times together with NCSoft in this year. Detailed analysis cases will be presented in other webinars. So let's start with the first topic, background and motivation of our solution. Let's talk about the overview of the composite first. You can see some examples there. This is very important because our product is focused on composite materials. Composite is something made of more than 2 types of basic material. By definition, composite can be found in form of liquid, fluid, or solid. It's important to remember that these materials are not chemically dissolved and they are separated at different phases. I guess the most common composite material is fiber-reinforced plastic. Fiber is applied to reduce the weight of the product because it has a very high specific stiffness and strength. Resin may be reinforced with filler as well. It is often used in semiconductor packages. Filler are mixed to create the optimum material properties to suit the product. In general, composite often refer to such materials that contain resins, but we define the material which has any non-homogeneous microstructure as composite. According to this definition, porous materials like foamed or lattice made by 3D printer are also a good example. Although lattice is often used to reduce weight, it has a potential for many applications because mechanical properties largely depends on the microstructure. I will explain in a little more detail later. Sometimes metal materials have also non-homogeneous microstructure, which has many holes, complex phase, or crystal grains distribution and so on. All of these materials can be subjected to analysis in our Multiscale solution. These are some of the applications from a more macroscopic viewpoint or at the actual product scale. The application that you are most interested in may be weight reduction. As you know, modern aircraft are made of carbon fiber reinforced plastics. As technology advances, metal materials such as steel and aluminum are being replaced by composite materials. Ceramics matrix composite are also used for the parts which requires high heat resistance such as a turbine blade. However, damage behavior is not negligible in these materials. We are developing a new function to support analysis of such phenomena. Talking about the medical industry, CFRP is used in equipment such as MRI for its excellent electromagnetic wave permeability. implanted materials like artificial hip joint and bones are constructed by lattice structures. Only the biocompatible materials can be used for such applications, so engineers control stiffness by utilizing the lattice structure without changing the material. The energy industry also has many products that are composed of different types of non-homogeneous structures. Wind turbine uses FRP to improve rotational efficiency. Sometimes pressure tanks are molded by filament winding using carbon fiber. In the rechargeable batteries, the shape of granular active material is optimized to increase the storage capacity and charging efficiency. Looking at the electrical industry, there are many products with the electronic circuit board that is made by using different types of non-homogeneous structure. For an example, substrate is made by FR4, which is a composite made from woven glass fiber and epoxy resin. Circuit board or PCB always contain fine wiring patterns, which can also be regarded as a type of composite materials from the multiscale analysis perspective. Then the semiconductor package are usually being sealed off with a resin. We add filler to optimize the material properties such as a volume fraction or size distribution and so on. So you can see that materials with inhomogeneous microstructure are used across many industries. I think that the designing of these materials are not only being done by material manufacturers, but also often being developed by manufacturers themselves. We are facing trouble for the simulation of such kind of materials. This is a scale problem. Composite has non-homogeneity in the viewpoint of submicron order. Sometimes we have to make a model for this microstructure because failure of unidirectional materials are started from the debonding at the interface between fibers and matrix. On the other hand, their structure made by FRP has very big scale comparing the microstructure, so it is unrealistic to make each fiber in real structure in terms of calculation cost. So, how we can resolve the problem? One of the answers is multiscale analysis approach. Macroscopic real structure will be divided into 3 types of scale problems, which is called micro, meso, and macro respectively. Microscale analysis is using the model which take into account non-homogeneity of fibers and matrix, as I mentioned now. We can observe the most strictly results, but its approach does not be performed due to large analysis cost except in special cases. Mesoscale structure is modeled as homogenized layer. Each layer has equivalent material constants for unidirectional materials instead. Furthermore, material principal axes for each element are also defined in order to take into account the fiber orientation. We can consider delamination phenomena at the interlayer by mesoscale model. So you should adopt this scale approach if you want to analyze of their failure and its modes are dominated by delamination. Macroscale structure is the most simplified case. All of the layers constructed composite are homogenized. We use equivalent material properties again. In this way, composite analysis can be cleared by replacing the real structure as homogeneous model which has equivalent material constants. Based on this analysis approach, I will present the challenges of composite material analysis. These are the motivation for using our tools. Here you can see is the results of survey conducted by NEFM's Composite Working Group. The question is, where do you need the most help when simulating composite? As you can see, many analyses have trouble getting material data for composite materials. Failure criteria and manufacturing, which are ranked second and third, are also problems that are essentially caused by material data. We believe that the efficiency in analyzing a composite can be summarized into three major problems, which are about material modeling, structural modeling, and post-processing, as shown in the figure at the right-hand side. Material modeling is items relating material constants needed for the analysis. The problem here is that composite has controllable property. I mean, since the material property changes dramatically depending on how raw materials are combined, the degree of freedom in material design increases, but it is difficult to make a general-purpose material database. Moreover, composite has anisotropic properties, so it is not possible to obtain all material constants required for analysis from only uniaxial tension tests like metallic materials. Structural modeling means definition of fiber orientation is tough work for us. Sometimes we have to carry out the analysis for molding processes because fiber orientation is depending on it. Final one is about the failure judgment. We cannot judge failure by only form is equivalent to stress due to its anisotropy. In other words, the successes of composite analysis is determined by how efficiently the properties are prepared. So, let me introduce our products for performing multiscale analysis. Firstly, let me show you about the overview of our multiscale solution. The tool name is Multiscale.sim. This product was developed to predict the equivalent material properties for composite using the homogenization method. In early stages of the development, the main purpose was to implement it on Ansys mechanical APDL. We continue to support up to date. Since all processes have their own defined commands, analysis can be performed in combination with normal APDL programs. Batch processing can also be performed in the same way as in the conventional procedure. It is also implemented on Ansys Workbench. All of the functions, such as the definition of virtual material test conditions and the evaluation of macroscopic material responses, can be performed on the application installed on Ansys Workbench as well. Hence, Multiscale.sim work with various Workbench products such as Design Explorer, Composite Prepost, and so on. This will dramatically expand the versatility of this product. Specific analysis examples will be introduced in more detail later. About the management of material data, the predicted material constants as a result of homogenization analysis can be registered in engineering data. So, data management is very easy. Working with GrantMI also could be effective if you want more advanced management and operation. Since the analysis results obtained by Multiscale.sim contain the same information as a physical material test, you can manage virtual material test data in the same way. What you can see here is a schematic diagram to explain the procedure for Multiscale.sim. Multiscale analysis adapted in our product divided the analysis object into two types of models, which are called as Microscale Model and Macroscale Model, respectively. Micro model is expressing non-homogeneity of the microstructure of composite materials. In the case of tire, the micro model is made by rubber matrix and carbon black filler. In the first step, we make microscale model for composite material. Here, only typical region of the microstructure is extracted as micromodel. Subsequent analysis assumes periodic symmetry conditions for the micromodel in all directions. By using this FE model, virtual material testing, such as uniaxial tension or pure shearing test, are also carried out in Ansys product. As a result, macroscopic material responses are obtained for each deformation mode. Finally, equivalent material constants can be identified by curve fitting its responses. Macroscale model is made by composite material, but its non-homogeneous microstructure is not modeled and homogenized by means of equivalent material constants obtained from previous step. In this way, the information between two different scales is combined via equivalent material constants. This analysis step is called as homogenization analysis. It is the most important feature for us and explained in more detail at the next slide. Finally, it is also possible to evaluate the stress distribution inside the microscale model by focusing on the part of the macro model. That is calling as a localization analysis, and it is also original feature of Multiscale.sim. I will explain the most important function of Multiscale.sim, which name is homogenization analysis. What you can see here is a schematic diagram to explain the procedure to evaluate the material constants using Multiscale.sim. You can get macroscopic anisotropic material constants as a result of this analysis without any real material testings. The steps colored in blue is input and red means the output information. In the first step, we have to make a FE model for microstructure of composite based on observational or presumed results. In this step, we provide many templates to create the microstructure which is embedded in the Ansys design modeler or Ansys space claim. The figure top of right is an example of microstructure created by design modeler template. You can create such kind of microstructure by just input the geometrical information like that. After creation of the model, we have to define the properties for each part constructing the microstructure. For example, fibers and lacings and so on. And then we perform virtual material test by FEM simulation for microstructure model. This analysis step is called numerical material testing generally. This is just an image of virtual material testing. For example, if you want to know anisotropic elastic constants, our tool performs the test for 6 deformation modes, which are uniaxial test, tension test, and pure shearing test for 3 deformation modes respectively. As a result, we can evaluate macroscopic material response as stress-strain curve, and then curve fitting analysis is performed in order to predict material constants for any material constitutive law. All of these procedures setting can be performed in Ansys mechanical GUI. So you cannot need to run new operational procedure if you are Ansys user. This output information, stress-strain curve is depending on the material behavior. If you evaluate creep or viscoelastic behavior, our tool output creep strain or stress-strain history curve respectively. I will show each feature in a little bit more detail. It is not realistic to make microstructure manually by general CAD tool due to its complexity. What you can see here is some of the microstructure which can be created using our tool. You can see on the left a model of the filler dispersed composite materials. Filler supports shape such as spheres and spheroid. The solid model is created automatically based on the geometrical information such as volume fraction of filler and so on. We provide many kinds of fiber-based composite. In particular, continuous fiber composite materials have a high affinity for homogenization analysis because unit cell model for these structures always have cyclic symmetry. These include unidirectional reinforcement as well as materials such as fabrics and knits. Simply, the microstructure of short fiber reinforced composite do not have cyclic symmetry. However, equivalent material constants can be obtained with a certain degree of reliability if the average information such as fiber orientation and volume fraction is well defined. Then we support lattice structures. people who are working on additive manufacturing may be interested in the Lattice. Once the Unicell model of microstructure has been created, it is used to conduct virtual material tests to obtain equivalent material constants. As you can see, Multiscale.sim allows you to identify the material constants for many types of material behavior. We already discussed an example for structure analysis, but our tool can obtain the material constants also for thermal, fluid, and electromagnetic analysis and so on. All material models support anisotropic behavior except for density and specific heat. It is also a unique feature of our product that it deals with a very wide range of problems. Basically, for all materials models, an appropriate virtual material test can be performed according to the material constitutive law you want to identify. Most of the cases, other than structural analysis, are treated as linear problems. On the other hand, various nonlinear material behaviors can be taken into account depending on the phenomenon considered. Typical characteristics are shown in the graph at the bottom. The most basic output is a stress-strain curve. You can check the response of composite composed of elastoplastic or hyperelastic materials. Only the tension side is shown here, but any load history, including compression side, can be defined. Creep characteristic and stress relaxation characteristics can also be acquired for any deformation mode. These tests can be very expensive in real tests because you have to observe the behavior for a very long time, such as days or years for the creep properties. Virtual material testing has a great advantage in obtaining such properties, which normally takes a long period of time in physical testing. The anisotropic material constitutive law and the curve fitting function for identifying the material constants all are provided by the user subroutine. As I mentioned at the beginning of the presentation, damage behavior is not negligible in some composite materials. Damages can be seen when the slope of the graph is different between initial loading point and unloading point. In other words, elastic constants are changed with increasing external load. We are actively developing anisotropic material constitutive law to expand the scope of multiscale analysis. We can confidently say that not so many tools can provide functions ranging from virtual material testing to curve fitting for such a wide range of problems. Up to this point, we discussed the basic functions. From here, I would like to introduce the features for coupling with Ansys Workbench product. Since Multiscale.sim is a completely add-in product to Ansys Workbench, it's a big advantage for us to be able to do this analysis easily. Analysis using Multiscale.sim are mainly performed on the Ansys mechanical GUI and design modeler or space claim for creating microstructure. Of course, you can import the data from external CAD if you want to create manually. As I have shown you so far, homogenization analysis focused on the very limited region to obtain equivalent material constants of composite. Limited region means specific layer in the case of laminated materials. It is effective to collaborate with Ansys Composite Prepost when you want to know the material property for laminated structure. Ansys Composite Prepost has a function to predict properties of laminated structure using stacking theory. In other words, you can easily obtain the material properties for any lamination pattern if you have prepared the material constants for single layer. Composite Prepost also provides a convenient method to predict the fiber orientation or cross angle after press molding. You can perform more accurate analysis of the product manufactured by press molding if you prepare the cross angle dependent material constants from homogenization analysis. In our proposed method, the link between microscale and macroscale is achieved by using equivalent material constants. Therefore, we can work with any FEM analysis tool as long as the material constants for material constitutive law required by other tools can be identified. Ansys LS-DYNA and Maxwell are examples for Ansys products which can be coupled with Multiscale.sim. It is very easy to link because these products can directly import material constants stored in engineering data on Ansys Workbench. We get that it is effective to register material responses and material constants obtained by Multiscale.sim in GrantMI if you want to manage the material database in a more advanced manner. Moreover, you can develop a case study simulation using various design variables by using it together with Ansys Design Explorer because all these coupled systems are implemented on the Ansys Workbench platform. This is an analysis example of the composite material considering the molding history. Figures on the left is an analysis example for resin transfer molding. FRP is created by pouring resin after molding a dry fabric. It is very important to predict the resin flow pattern during the pouring process. This is because we can consider the cause when we find the molding defect such as residual void or warpage and so on. The flow pattern can be confirmed by resin flow analysis. However, we have to remember that there is a dry fabric in the casting mold. Anisotropic flow resistance is distributed due to the presence of dry fabrics. To make matters worse, the density and orientation of the fibers are influence the flow resistance depend on the molding history of the press molding process. That's why we have to perform the analysis for press molding. Mechanical properties of dry fabrics are very unique and tends to increase sharply from the particular cross angle as seen here. In the real test, the measurement can be performed by the picture frame test as shown in the figure, but this can also be performed using virtual material test of Multiscale.sim. This material behavior can be expressed by LS-DYNA's material constitutive law specialized for dry fabrics. On the other hand, material constants for flow resistance can also be predicted by homogenization analysis in Multiscale.sim. Flow resistance as a functions of volume fraction and cross angle of fiber are predicted. And then, the distribution of flow resistance is mapped based on the results of a press molding process. This makes it possible to perform the resin flow analysis for the press molding process. Figures on right-hand side shows an example for the product made by injection molding. Also in this case, the direction and the density of fibers change depending on flow state. The fiber orientation is not uniform and it is always distributed within the single part. In our approach, material constants at the previous fiber orientation tensor are prepared in advance by homogenization analysis. These properties are expressed as a response surface in functional form for orientation, as shown on the upper right. Distribution of material constants are mapped depending on the fiber orientation, which is predicted by resin flow analysis. By using this method, it is possible to carry out structural analysis of injection molded product, considering various inelastic behaviors. As a next, I'd like to talk about the collaboration with GrantMI before showing the specific analysis example. Let me introduce the benefits we can gain from the collaboration with GrantMI. Any information obtained from material testing can be managed centrally by GrantMI. Now, we have two choices on how to obtain the material data. In other words, real material testing and virtual material testing. So, let's first consider the differences between these two testing approaches, looking at the cost. In the case of realistic material testing, It always takes time and effort to prepare the test pieces prior to conducting the test. This task may not be easy because it involves a lot of steps such as preparation, molding, and cutting, and so on. In addition, in some cases, you may need a jig to hold the specimen in place. I guess that it will take a few days even of only advanced preparation phase. Needless to say, the real testing will be hard work as well. In particular, obtaining time-dependent material behavior such as creep or fatigue can take a long time for testing. When this test is conducted under different conditions, the cost increases in proportion to the number of test cases. On the other hand, what about the virtual material test? You will still need to create the model corresponding to the specimen. However, model creation can be completed in a very short time by using the template as I mentioned before. A jig is not necessary because the boundary conditions can be simulated. And with analysis, the time cost is independent of the time range you want to observe. We don't need any additional cost to repeat the material test with various conditions. Moreover, all these iterations are done automatically, so it is making GrantMI a great match for storing big data for material testing. I will show you the importance of accumulating the material data using a simple image. In the case of traditional material design methods relying on real testing, the cost increases linearly with the number of test conditions. As the number of case studies increases, the burden on the material design phase will grow more and more. Replacing real tests with virtual material testing can dramatically improve design efficiency because the cost per test can be reduced. Here, it should also be important that the whole process from test execution to evaluation be done automatically. While the introduction of virtual material testing will result in no small amount of cost savings, let's take one more advanced step. It means the test data will be centrally managed in GrantMI. Once the sufficient amount of test data has been accumulated, a new design phase can be introduced, that is, data-driven material design. It refers to that match the desired properties. By combining response surfaces or AI technique, we may be able to have new composite materials suggested to us that are not in existing material databases. By adapting this data-driven design, we can expect even more dramatic cost savings. Probably, data-driven material design cannot jump up from real testing without going through the virtual material testing phase, especially in the case of composite materials. This is because the material database measured by real test is generally still insufficient. As a last topic, I'd like to show some of the use cases for multiscale analysis. First, let me share some examples for validation and verification. We have also conducted real material testing with our coworkers. When we release new functions, we make efforts to validate the analysis accuracy by comparing the results of real test and virtual test. Many of the analysis cases are for fiber-based composite materials. The first one is an example to predict anisotropic elasticity and thermal expansion coefficient for glass-cross materials. Geometrical information for microstructure needed for homogenization analysis was identified from the observational results by scanning electron microscope. The result shows material constants for three normal directions. X and Y means direction for fiber orientation, and the Z-axis means out of plane direction. Young modulus for fiber direction has always high value since the modulus of fiber is much higher than epoxy resin. as matrix phase. On the other hand, thermal expansion coefficient shows the opposite magnitude relationship. This is because glass fiber has extremely low thermal expansion coefficient. As you can see, all material constants obtained by homogenization analysis are similar with experimental results. We could not perform Young modulus for out-of-plane direction due to thick shape of the specimen. The ability to get material properties in such a direction is also an advantage of virtual testing. The ability to get material properties in such direction is also an advantage of virtual material testing. In addition to the material constants, we also compare the results with real test. This figure shows the example to observe strain distribution by means of DIC, which stands for Digital Image Correlation Method. In this case, we prepare notches with different positions on the front and back of the test piece. When compressive load is applied from the in-plane direction, a region where pure shearing mode dominates can be observed between the notches. We confirmed that the strain distribution quantitatively agrees with the real test by preparing the accurate anisotropic properties. We collaborate with Shimazu Corporation to create this example to validate the shear properties. The picture at the bottom shows the test results for the collision problem. The indenter collided at the speed of 40 km per hour from the CFRB in plane direction. We are comparing the load history graph at that time. You can see that there is a good correlation between the load rising tendency or the fracture timing obtained by real test and virtual test. In this analysis, the state of fracture was also observed with the high-speed camera, and it was confirmed that the state of fracture was similar to the analysis. Next one is about the analysis example for materials other than FRP. The top figure is an example of conductive adhesive, which is considered as an alternative to solder. The epoxy resin that constitutes the matrix does not have a good electrical conductivity, so the conductivity is improved by mixing the silver filler into the resin. We created the model for microstructure based on the image observed by X-ray CT, since the shape of the silver filler is not simple. This image processing cannot be performed by our tool. We use another software called Simpleware sold by Synopsys. We compared the inelastic stress-strain characteristics of the composite state. The last one is an example of predicting the elastoplastic properties of metallic materials. As you know, the shape of metallographic structure depends on solidification conditions such as cooling rate. In this analysis, the metallographic structure of cast iron was roughly classified into 3 types, and the material behavior of each structure was simulated. We managed to get good analysis results compared to the real test. This is also important analysis case. As discussed in the previous topic, in the case of FRP, the material properties of the fiber and resin need to be prepared prior to analysis. Among them, we have to care material property for carbon fiber. It is well known that carbon fibers have anisotropic elasticity. Young modulus for longitudinal direction and radial direction is not the same. Shear modulus and Poisson's ratio also have 2 independent properties respectively. We can only obtain Young modulus for longitudinal direction, whereas all other components are impossible to perform real material test. This is because the radius of carbon fiber is very small, it's like a human hair, so we cannot hold the specimen in order to perform the tension test for radial direction. Such kind of properties should be identified by comparing real test and virtual test. It can be realized by inverse analysis. Detailed procedures are illustrated at the right-hand side. A final goal of inverse analysis is that obtain all components of anisotropic material constants of carbon fiber based on the composite properties, which is measured by real testing. In this analysis approach, we have to use smart artificial intelligence. So before solving inverse analysis, artificial intelligence have to be learned by a large amount of training data. These data were obtained from general homogenization analysis. We input the properties of carbon fiber as any value because it is unknown value at first. The composite properties as a result is not matched in the real case, but we do not need to care about it. This is used just as training data. This series of operations was repeated with changing the fiber's parameters. Based on these big data sets, we make smart artificial intelligence and used for inverse analysis. We would like to examine the validity of the material properties identified by the inverse analysis approach. It was also confirmed by cross-validation process. In this case, we specify the material properties of carbon fiber as any value as well as running phase. Then we get the equivalent material constants for composite. On the other hand, in the case of inverse analysis, we use the composite material properties, that is the results of previous step. If learning for neural network is enough, the results of inverse analysis should be similar with the input value of numerical material test. Actual comparison results are shown in the table. As you can see here, the error rate between input value and the results of inverse analysis is very small. Of course, the prediction accuracy will be more improved with increasing training data. I guess it is difficult to make such large data set by only real testings. Homogenization analysis is ideal for making the large amount of training data. Lastly, here is an example of analysis for the lattice structure. At here, we used a simple two-dimensional lattice structure model as an example to observe the relationship between lattice shape and Poisson's ratio. The photo on the left is an example of conducting the tensile test on the lattice structure in the vertical direction of the paper. Please note that the width is not changed during the tension test. This material has almost zero Poisson's ratio. Such properties cannot be created unless the material has an inhomogeneous microstructure. Therefore, we investigated the relationship between the shape of the lattice structure and the macroscopic Poisson's ratio using Design Explorer and Multiscale.sim. We set two design variables in the model of lattice structure for homogenization analysis, the angle and the thickness of the columns that makes up the lattice. You can see the results and confirm that the macroscopic Poisson's ratio is very sensitive to the angle of the column. I have also included the cross-section graph at specific thickness values. You can see how the Poisson's ratio widely varies from 0 to 0.5 when changing the angle of columns. Deformation shapes during virtual material testing for three representative design variables are also given here. So you can see the reason for the changing of macroscopic ratio. We also verified these analysis results. Since we could not perform real test, we compared the analysis results of the macroscopic coupon test model with the equivalent material constants and the case where the non-homogeneity of the lattice structure is actually modeled. Results of homogenization analysis could be verified since the deformed shapes of two models are closed. We extended the analysis target to 3 dimensions. We set 3 kinds of design variables as shown here. There are many kinds of topology in lattice. This time, 30 pattern of lattice topology is adopted. Porosity and height of unit cell are set as geometrical parameter. The raw material used to construct the lattice is assumed to be titanium. Please note that the material has never been changed. The graph shown at the left is the results by plotting material constants in which horizontal and vertical axes are adopted as Young modulus and shear modulus for in-plane direction respectively. Different shapes of plot means difference in lattice topology, and color means the value of porosity in unit cell. We can confirm that both Young modulus and shear modulus are increased with increasing thickness of columns. However, we can see that it can be classified into 2 points clouds with different characteristics. One has a high sensitivity of Young modulus, and the other has a high sensitivity of shear modulus. The overview of the model and the equivalent stress distribution on the deformed shape are shown for one representative point belonging to each cluster. The model at point A has many columns oriented diagonally with respect to the tensile direction. At point B, there are no diagonally oriented columns, and all are oriented in the tensile direction and its vertical direction. It can be seen that the stress is concentrated on the columns parallel to the load direction during uniaxial tension test and on diagonal columns during shear deformation. In this way, the elastic modulus of the lattice structure strongly depends on how the columns are oriented. Poisson's ratio shows more complicated characteristics. It changes in the drastic manner depending on the lattice structure. Now, let's take two design conditions as an example to show what kind of deformation is being made. Point C has a Poisson's ratio of the out-of-plane component that exceeds to 1.0, whereas the Poisson's ratio of the in-plane component is almost 0. Actual lattice structure is shown here. As you can see, that there is almost no change in the y direction, even if the specimen is pulled in the x direction. This is because the diagonally oriented column moved to outward in the y direction when they shrink in the z direction. On the other hand, when tensioning in the y direction, the diagonal columns moved into the direction of reducing the thickness. In this way, geometrical rotation of each column strongly affects the macroscopic Poisson's behavior. Poisson's ratio at point D is also changing by the same reason. In this structure, despite doing tensile testing in the x direction, the model extends in the y direction as well. This means negative Poisson's ratio. We need to prepare the large material database in order to make the best use of the characteristics of the lattice structure. These processes can be achieved efficiently by virtual material testing. So, we are reaching the end of today's presentation. This slide is summarized what we discussed today. Our product has three main functional features. It is homogenization analysis, localization analysis, and usability. Among them, homogenization analysis is the most important feature, and they consist of microstructure creation, virtual material testing, and curve fitting. All of them are feature-rich, and we are confident that they are comparable to the other competitive product. We also provide localization analysis, although I have not able to show enough use cases for this today. Usability is excellent as well, especially if you have an operational experience of Ansys product. Our products are add-in tool to Ansys, so you do not need to practice any new GUI. In addition, it is highly compatible with other tools implemented in Ansys Workbench, such as Ansys Composite Prepost, Design Explorer, GrandTimer, and so on. Please contact NGSoft or us if you are interested in any of the features. We will be happy to provide you with a free 1-month evaluation license. Let me share some other references. We have presented this product in 2 Ansys Inc. webinars in the past. Both of them are registered in Ansys Inc. resource library. Please take a look at this page as it introduces different analysis examples from today. The latest news about this product can also be found on LinkedIn. We hope you will feel free to follow us and refer to it along with our website. This concludes my presentation for today. Thank you very much for your attention, and we are looking forward to working with you. Goodbye.